Started. Good morning, guys. Today we're going to be finishing up our course, wrapping up our discussion on radiation heat transfer, as well as having a brief discussion and review in preparation for the final. So last time we were discussing radiation heat transfer. Which really just kind of felt like a sciencey lesson, but we said for radiation, we can calculate our radiation heat transfer rate as epsilon sigma a sub s ts to the fourth minus t infinity to the fourth, where epsilon was our emissivity, sigma was our Stefan-Boltzmann's constant, which was 5.67 times 10 to the minus 8 watts per meter squared Kelvin to the fourth. We looked at some discussion on the emergence and development of this as it comes from Stefan-Boltzmann's law. I'll just say FB's law, where our blackbody radiation or emissive power, EB sub t, is quantified as sigma times t to the fourth. Or for a non-blackbody, E sub t, we calculate it as epsilon sigma times t to the fourth. Then from there, we discussed spectral blackbody emissive power, which is from Planck's law, which stated, now we're interested in our emissive power as a function of both wavelength and temperature, where we found that expression of C1 over lambda to the fifth times the exponent of C2 over lambda t minus 1 with units of watts per meter squared microns to the fourth. Oh, per micron. Actually, let me double check that. I had issues with that in my notes. I want to make sure I tell you right. It's per micron. So with that, C1 was 2 pi times Planck's constant times C naught, which is 3.742 times 10 to the eighth watts microns to the fourth over meter squared. And C2 is H C naught over Kelvin times 1.439 times 10 to the fourth micron Kelvin, where K was Boltzmann's constant. Here, I'll zoom out. (1.38065) times 10 to the minus 23rd joules per Kelvin. Any questions of this at this point? All right. And at the end of class, we talked about looking at a graphical representation of Planck's law.
Dr. Lopez, should those exponents be negative or are they supposed to be positive?
For C1 and C2, they are positive.
Okay, thank you.
Of course. And so looking at the graphical representation of Planck's law, we find that we have a maxima associated with emissive power at particular wavelengths. And as we increase our temperature of our object, the wavelength associated with that maximum decreases, which means the higher energy an object possesses is, represented by the temperature, the lower the wavelength of radiation that's emitted. Or we can look at this locus of maximum power designated by the slope, which gives us a slope lambda t of 2898 micron Kelvin, which is essentially stated via Wein's displacement law. So basically just for Wein's displacement law, lambda t max is 2897.8 micron Kelvin, where lambda max is just 2897.8 over t. And this will give you microns. And the last thing to touch on this is looking at the integration of Planck's law. So if we integrate Planck's law, 0 to infinity, what we're left with is Stefan's Boltzmann law, or sigma times t to the fourth. Which, all well and good, nice and slightly helpful. But if we're interested in determining the emissive power over a range of wavelengths, or EB sub lambda t from lambda 1 to lambda 2, what we do to identify that is look at EB lambda t from 0 to lambda 2 minus lambda 0 to lambda 1 of EB lambda t lambda. So what you look at is taking the integration from 0 to each wavelength and doing a subtraction. And what that gives us is what's known as the emergence of what we call radiation functions. And so what we say this is essentially f of lambda 2 minus f of lambda 1 times sigma t to the fourth, where f lambda sub I is a radiation function. And to find a radiation function, we simply rely on a table where, given an object's temperature and its wavelength of interest, we can find the product associated with that two values, and the associated wave radiation function can be identified from a table. So for example, if I had an object if I wanted to look at the fraction of radiation emitted between 1 and 5 microns for an object, at 1000 Kelvin, I would say my lambda, f of lambda 2, would be lambda 2 times T, or 5 microns times 1000 Kelvin, or 5000 microns Kelvin. And my f lambda 1 would be lambda 1 T, or 1 micron times 1000 Kelvin, or 1000 micron Kelvin. And so what should I get for my radiation functions for these values? So what I need to look at is my value associated with 1000 micron Kelvin here and 5000 micron Kelvin, which is here. So at 5,000, I have 0.633747. At 1,000, I have 0.000321. And so what I have for F lambda 2, lambda 1 is 0.633747 minus lambda 1, which is 0.000321. Or 63.3% of my total emissive power will fall within that range of 1 and 5 microns. Now everyone follow that along, okay. If so, let's take a look at a couple other examples. Let's look at this one first. So in this example, I have a 20 centimeter sphere at 750 Kelvin. It's going to be suspended in air. If I can assume it's a black body, what's the total emissive power? The total amount of radiation emitted in 5 minutes, the spectral blackbody emissive power at a wavelength of 3 microns, and the wavelength associated with the maximum energy emission. So let's take a look at this example together. So example 1, we have a 20 centimeter, or say 0.2 meter sphere. It's a black body. So its emissivity is 1. So we're looking for the total spectral emissive power. So our EV sub T is simply sigma times T, or 5.67 times 10 to the minus 8 watts per meter squared, Kelvin to the 4th. The temperature, given as 750, and I need the surface area of a sphere, which I believe is pi d squared. Yep, or pi times 0.2 meters squared. And so this should give me units of watts.
Shouldn't the temperature be to the 4th?
You are correct. Thank you. I knew something wasn't right. So let's see what this gives us. So I got about 2,254 watts. So if I'm looking for total energy emitted in 5 minutes, so I have 2,254 joules per second. So that's what a watt is in 5 minutes. And there's 60 seconds in 1 minute. So I just multiply my answer times 5 times 60. And I'm left with 676 kilojoules. The next question asked about the spectral blackbody emissive power. I have a wavelength of 3 microns. So for this, I have to look at Planck's law. So I'm looking at AB, some 3 microns, T is 750. So I have C1, which from my notes is 3.742 times 10 to the 8th watts microns to the 4th per meter squared, divided by lambda, which is 3 microns to the 5th, times the exponential of C2, which is 1.439 times 10 to the 4th micron Kelvin, divided by lambda and T, or 3 times 750 micron Kelvin, minus 1.
Hey, Dr. Lopez, I'm following along with the PowerPoint. It says the powers on those constant terms are negative.
Let me double check. Yeah, they should be positive. So I will fix the PowerPoint right after class. So let's see what we get with this. So I ended up with approximately 6,986 watts per meter squared micron. You guys can double check that if you want.
Got a different answer.
What did you end up with?
2,574.
Well, I'm using a very crappy calculator, so I can pull it in Excel. Slightly
I got
better.
that as well.
The 2,000?
Yes, sir.
All right. It's probably my order of operations on my calculator. So it always helps to double check. Help if I put the equal sign in. Yeah, 2586.
My answer is close, but not quite. I'm not sure what I did wrong then.
That's fine. All right, so about 2586 watts per meter squared micron. And then the last part of the question asked was the wavelength associated with the maximum energy emission. So with that, all you need to look at for lambda max is White's displacement law, or 2897.8 micron Kelvin divided by 750 Kelvin. That I think my little calculator can handle. I get 3.86 microns. Now, any questions on that example problem and how we could use Planck's law and Stefan Boltzmann's law to find our emissive power in terms of total emissive power and spectral emissive power as a function of wavelength? All right, if not, let's look at one more example really quickly. All right, this one's looking at the temperature on the filament of an incandescent light bulb is 2500 Kelvin. If we assume the filament is a black body, what's the fraction of radiant energy emitted by the light bulb that falls within the visible range, the energy emission within that range, and once again, the wavelength at its peak emission? All right, so this is looking at a light bulb. The temperature is 2500 Kelvin.
We're still on the PowerPoint.
Yeah, I'm about to flip it back. So visible range is approximately from 0.4 microns to 0.76 microns. And so the total fraction, what we're looking for is f of lambda to lambda 1, or f lambda 2 minus f lambda 1.
Dr. Lopez, how did you know those wavelengths?
It asked about visible light, so I can Google it, or I can refer to my notes. And so lambda 2t is simply 0.76 microns times 2500 Kelvin. Which is approximately 1900 micron Kelvin. Lambda 1t is 0.4 microns times 2500 Kelvin, which is about 1000 micron Kelvin. So going back to my table, my radiation functions, once again I have 1000, but I'm also looking at 1900. Let me zoom in a little, if it'll let me. So I have 1000 and 1900, so I'm going to have to interpolate between 0.0667 and 0.0393. So if I do that, I get F lambda 2 equal to about 0.053035. And F lambda 1, I was able to get directly from the table. It's 0.000321. And so F lambda 2 to lambda 1 over that range is simply 1 minus the other, or approximately 0.0527. 135. I really don't care about those sig figs. So really only percent, 5.27%. So about 5% of the energy emitted falls within the visible range. The next part of the problem asked about the energy emission within that range. So for that, I'm looking at AB. So lambda 2, lambda 1, T. So all I need is essentially 0.0527135 times sigma, which is 5.67 times 10 to the minus 8 watts per meter squared Kelvin times the temperature, 2500 Kelvin to the 4th. And this will give me the energy flux in that range. So we do that and we get approximately 116,752 watts per meter squared. So that gives us our flux. The last question asked about the peak wavelength, which once again, going back to our lambda max, 2897.8 micron Kelvin divided by 2500 microns gives us a maximum wavelength peak of 1.16 microns. From that, it peaks somewhere in the infrared region. So any questions on that example? You guys follow along okay? I see some head nods, a lot of dejected faces. I get it. I understand. Hang in there, guys. You're almost there. All right. So that wraps up our discussion on radiation, as well as all of the topics that I have for you here in fluid mechanics and heat transfer. So great job, guys. You made it through 12 modules, 18 lectures, many hours and homeworks and all the things.
Only 18?
It was only 18 lectures, yeah. It just seems like a lot. Especially if we talk about all the topics that we've discussed in this class. It's a lot. It is a lot. So let's talk about your final exam. So if my memory serves, your final exam will be on Tuesday, November 24th from 8 o'clock a.m. to 11 o'clock a.m. It will be on Zoom. And for now, I will require you to be present with camera for full credit. If you don't have a camera or if that's going to be an issue, please let me know. Just because if it was going to be an actual final, it would be proctored. And if it was going to be virtual, it would have to be through some third-party software, and they would most likely require a camera as well. And so I don't require it in lecture. I haven't required it in the midterms, but for the finals, since it is the final, I'm going to have that rule.
Can we still use like your PowerPoint slides if we have those on our laptops? We're taking that.
Yeah, that's fine.
Okay.
Yeah, I can't lock it down that much just because I can't police that. There's only so much I can do, and I really don't like being a hard ass. Nobody likes that. And like I said, I think a 3-hour restriction's enough. And if, yeah, I'll keep that in mind when I design the final, because you will have essentially access to the lectures and the notes and everything. And so I thought the first 2 exams were pretty good in terms of difficulty and length. You guys actually did surprisingly well for the length that was that second midterm. I was anticipating more difficulty from you guys in terms of getting it done, but I only had a very small handful of people that had trouble. And so you can expect about what you saw in those first two midterms on the final. So, 5 to 7 questions, 100 points, right? It is worth 25% of your total grade. So yeah, definitely keep that in mind. And it will be a cumulative final. So it will cover everything over the entirety of the course. I will emphasize the last, section, last third of the classroom material. But other than that, it will cover everything. All right, so before we jump into it, are there any questions?
I think earlier in the semester you said it'd be a good idea to have the properties for air and water that we might need on an equation sheet.
That's true.
Okay.
But we will be able to Google those if we need them, or like engineering toolbox.
Yes. I will not answer questions associated with air and water properties. That is a good question. A very good question.
Would you answer them before, like if we were studying, say, this weekend and we asked you if this was a viable value for one of them, would you answer it then? Like if we were making like a sheet of everything.
Oh, of course, yeah. If you wanted me to
okay.
review anything like that, I'd be happy to, yes.
Okay, thank you.
For the current So on Blackboard, you have the breakdown of the grades. Are those constantly updated, or do you have to go in and update those?
I have to go with it and update them. I will try to update them by the end of the week. I'm still working with with the graders to try to get some of that figured out, because I know there's a couple things that haven't been updated. But my goal is probably by Friday, send y'all an email and be like, hey, your grade as it stands. I'll probably make a new column and just be like, this is your grade as it stands, so that you guys can do the calculations of, what do I need to make on a final to keep my A, or, to make a B, those kinds of things.
Dr. Lopez, I have a specific question about constant values. On the last homework, you gave us a baffle cut, and then I couldn't figure out how to find FB, so you told it to me in your office hours, but where should we go to find an FB from a baffle cut?
I will have to give that to you because it's kind of like a manufacturer specified value.
Okay.
Because it really depends on the type of exchanger and the design of it. What kind of baffles are you having? All of that's going to influence what that S sub B value is. And so there's no really good way to just quickly and easily look that up. So yeah. All right, so what other questions do you have? Because I can ramble for 10, 15 minutes to kind of get you to where you want to be and give you a quick rundown. But like I said, this is your time, and so I want to make sure that you get the information and I can answer the questions that you have.
Could you post like some sort of like topic list on like the important stuff to expect on the exam?
Maybe. I could. I've also thought about having like a review session on Wednesday, but that's like during finals week, and I don't know how you guys have your finals set up. Zach, you asked about a practice exam for the final. I can jot that down. I may have a practice exam I can release. I'm not 100% sure. It might. If I don't, I probably won't be able to do one because I will have to make 2 finals this year with the 2 sections, but I can take a quick look.
Would it be possible to do a review session over the weekend since you don't want to do one on Wednesday because that's while some people might be taking finals?
That would be a little difficult. Let me take a look and see what I have for practice finals. And if it is a reasonable practice final. Yeah, I can post a practice final if it'll help. May or may not help. I think the best thing is just to review all the homeworks. I will most likely post homework solutions Wednesday or Thursday. I'll send an email out, so make sure if you've got any, well, outside of homework 12, of course, but just make sure if you have anything.
So do you think studying the homework is better than studying those 2 past exams, or which ones?
The 2 PACS exams will help you a little bit in terms of just making sure you understand everything. Because I do like to say, okay, what did people struggle with on the midterms and put them on the final also. I'm not above that just because there's no point in it. Let's say everybody got a 95 plus on a problem on the midterm. There's no point in me putting it on the final because you all have demonstrated that you understand the concept. And so while it's helpful for a, everybody getting an A kind of standpoint, it's not really beneficial in terms of actually assessment.
Do you have any idea on what will be like the breakdown between like conceptual versus hard work problems?
It will be much more heavily skewed on calculations. I would say no more than 20% of this exam will be conceptual. And what I can say is you should probably expect 1.5 to 2 pump calculation / pump curvy type problems. I would most likely not put compressible flow on a final just because of all the things I would want you to get out of this class. Those equations aren't on my top 10. I would expect to see maybe something on packed bed, fluidized bed flow, and or continuity equation, just because that's really important in terms of you really can't do anything fluid mechanics wise if you don't understand continuity equation / Bernoulli. I like problems like that where you have to kind of combine those. But at the same time, it'll very heavily skew on heat transfer. So I wouldn't put it past myself putting something like, a transient conduction problem, a really good convection problem, and you'll definitely see a heat exchanger problem. I might, in the past, I put boiling and condensing problems on because they're good points and that in general, people either get it or they don't. There's not a whole lot of in between. Because if you know what you do, it's just plugging in the values for the equations and moving on. If you don't know what to do, then I don't know, you're in trouble, or I guess you spend the 3 hours looking through all the lectures to try to find it. The bonus usually either comes from that section or the radiation section, just because the radiation section's weird and it's kind of last minute. That kind of stuff. So that's what you should expect to see for the final. I've been known historically to throw a curveball, literally a problem about a curveball that trips students up. Trying to think of what else, but really that's what you should expect. Continuity, Bernoulli, nice long mechanical energy balance, pump problem, something to do with pump curves, system curves, and equipment. Something associated with packed beds, maybe finding pressure drop per unit length, those kinds of things. Transient conduction, just because that's one of those, if you really understand the problem and the equations, you can do well, and if not, it's really easy to tell. And then, of course, you're going to see a heat exchanger problem. And so I would definitely expect that. And then you might see something in terms of another deeper dive on convection, boiling and condensation, and if there's radiation, it'll be a bonus. So I think that would make a good final. Any other questions?
Just to clarify, are you going to be in your office hours on Wednesday, even though it's technically an exam day? Because I know we have design tomorrow during your office hours.
I can be.
Okay.
And if you can't find me, send me an email. Track me down. I'm technically at a conference also this week, so I might be annoying to find and get a hold of because I have duties associated with that conference, but it's virtual, as in all things in our lives these days. So I can probably swing office hours on Wednesday, for sure. And as always, if you have questions gearing up, getting ready, by all means, feel free to reach out. Anything else? And if not, I'll let you guys go. I appreciate you all. I hope you've had a good semester and that you've enjoyed this class to a certain degree. And I hope to see you in a future class, aka Design 2. So good luck to everybody in their finals. Good luck to everybody, the seniors, as they get ready for Adam's design final. Yeah, that's a final. And take care, guys, as always.
Have a good one.
You too.
Thank you, Dr. Lopez.
Thank
You are welcome.
Thank you.